Okay, so today's announcements are the Chapter 3 sapling is due 9 a.m. next Friday because I'm going to finish it up today. And then recitation quiz next week, that should say. So recitation quiz is going to be in your recitations Monday and Tuesday next week. Expect an emphasis on the stuff that people had a harder time with on the exam. So like the arrow pushing stuff on the first page is going to make an appearance, plus the stuff I'm covering today. And then exam regrades are due 9 a.m. next Wednesday. Just to let you guys know, I'm actually going to be out of town for the next week. So the guy who's covering lectures for me, Garrett Cairo, is an advanced TA who's taught for me before. He's going to be teaching lecture. You can either turn the exam regrades into him or just put them into my mailbox outside the organic labs. But either way, the deadline for those is 9 a.m. next Wednesday. And then when I get back at the end of the week, I'll grab the stack and go through it and then decide how to deal with the regrade requests. And for anyone who missed it on Wednesday, the way to submit an exam regrade request is staple a sheet of paper on the front saying what you want looked at why. Keep it brief, but enough that I can figure out what sort of explanation you're using. And then I'll sort of go through all of them once I have the stack, once the deadline's passed. Oh, and then also if you missed lecture on Wednesday, I have this stack of unreturned exams in my office. I'll have it at the help room hour immediately after this lecture, and then after that I'm going to parcel them back out to the TAs so you get it back in recitation next week. So one way or another, you've got at least 3 chances to pick it up from me before the regrade request closes. Okay, questions about those? Okay, cool. Alrighty. So we've spent the rest of Chapter 3 looking at a lot of acid and base stuff. Whether that's Lewis, acid or base, in other words, nucleophile or electrophile, or Bronsted-Lowry acids and bases. The last part that we're going to look at is how to figure out how acidic 2 things are relative to each other just based on looking at the structure. So relationships between structure and acidity. Okay, so Loudon does kind of an incomplete coverage of this. Textbook covers 3 different parts of this, and then the other 2 pop up later on in the book, and then you just sort of have to like remember all 5 of them from like different places. I kind of like covering all 5 at once because, for one thing, it makes it easier to keep it all in one place, and also it's kind of a fun acronym. Okay, so before we get into that, okay, so we know that lower pKa is a stronger acid. So the lower the number is, the easier it gives up a proton, the higher the pKa is, the higher the Ka is, and the lower the pKa is. But it turns out that a lot of the time what matters for acidity is not like the structure of the acid itself. What matters the most is actually the structure of the conjugate base. So stronger acid, lower pKa. We already know the stronger the acid, the weaker the base. And what really determines how weak a conjugate base is how stable it is holding the negative charge, if there is one, after it loses a proton. Okay, so for example, if you have, and we're going to cover this example in more depth in a second, but say you've got these 2 things. That's not it. That should be an equilibrium arrow. Jeez. Okay. So the pKa values that we give you in the tables might be this one, which is 4.76, and this one, which is about 16. But what really matters is not the structure of the acid itself, which is the part that we list in the table. What really matters is how happy the base is holding its negative charge. Turns out that this one is a lot less happy about holding a negative charge for reasons we'll get into. which means that it would strongly prefer to get its proton back and turn back into its conjugate acid. So this is a less stable negative charge, stronger base, higher pKa. So really, if you want to sort of save yourself a few steps of reasoning here, you can think of the pKa as a rating of like how strongly the base wants to get its proton back. So like this thing has a pKa of 16, it like pretty strongly wants to get its proton back and go back to being the neutral form. This thing has a pKa of about 5-ish. It is pretty okay holding a negative charge. Not as stable as some other things that we'll see with a negative charge, but it's a lot better than this guy is. Yeah? So pKa tables always list the acid form, not the base conjugate form. And so whichever way you draw it, like left to right or right to left, it's still looking at whichever form still has the proton on it. Mm-hmm. Okay, I guess like if you've got an amphoteric thing like water, it could list two different pKas, one for where it's going to, going from the conjugate acid to the molecule itself, and then one from the molecule to its conjugate base. Okay. So, how are we going to figure out how stable the negative charge is on these molecules, if there is one? So the acronym that covers all the points, I guess, to remember here is CARDIO, which stands for, yeah. So charge, atom, resonance. This one is a little bit of a kludge, but dipole, induction. Gets 2 letters, I guess, just to make it work. Otherwise, it would be cardo. And then orbitals. Okay, so we got 5 different factors to look at here. All right, so first one is charge. And by the way, these are sort of listed in decreasing order, but there's a lot of overlap. So sometimes, like, if you're comparing 2 molecules and one of them is better in the charge category and the other is better in the atom category, it might not be possible to make it a comparison between them. So usually if I'm asking you to compare 2 things, they'll be similar in every way, except for one of them might be better in like one particular category than the other. Otherwise, you would have to go to the pKa table and look it up if it's in there. Okay, so charge effect. Having a positive charge on something, and specifically having a positive charge on the acid, means that it becomes neutral when it loses a proton. So neutral base form. And if you have a neutral acid, it goes to negatively charged base. So ideally, we want things to be neutral to be as stable as possible. So having a negative charge at all automatically means the base is going to be less stable, which means that it's going to be a higher pKa. Oh. Man, I don't know if you guys can hear that from there, but this thing like squeals really loud up close. Okay. All right, so for example, H3O plus, if we show this losing a proton, it just goes to H2O versus H2O. If it loses a proton, it goes to OH minus. So we know that this thing, the conjugate base, is neutral. We would expect this to be more stable, which means, do we expect H3O plus to have a higher or lower pKa than H2O? Lower, good, yep. And that's exactly what we see in the tables. This is negative 1.7, and this is 15.7. So pretty much if something's positive charge to begin with, it makes sort of intuitive sense that it would be able to drop a proton off it a lot more easily than if you have to pry it off and make a negative charged conjugate base afterwards. Okay, so questions about that one? Okay, cool. So second up is atom effect. And we'll see other examples in which a particular atom will change the acidity. But this one is specifically referring to the atom that loses a proton. So if it's further away from the acidic site, as we would describe it, then it's actually doing something else that would fall under dipole effect, which we'll cover, or dipole induction effect. Okay, so in the periodic table, it's actually going to follow kind of a regular trend. So I'm going to put up some molecules here. So carbon, CH3, losing a proton off of it, has a pK of 60. So you can pretty much like show all of these atoms in the periodic table with a full set of protons and show the one that's coming off. We already know water is 15.7. HF is 3.2. And the ones for the lower end of the halogen series actually vary a little bit from source to source just because they're so acidic that it's actually a little hard to measure. They more or less go completely 100% losing their proton with like a tiny bit of leftover. Okay, so in general, we can sort of summarize the trend as moving left to right makes you more acidic. And then also moving top to bottom makes you more acidic. Okay, so this might be causing you to raise your eyebrows a little bit because if it's based on negative charge stability, why doesn't it just correspond to electronegativity? Like if it were just charge stability, you would expect, or if charge stability just depended on electronegativity, you would expect them to get more acidic this way because fluorine's the most electronegative, but you would also expect HF to be the stronger acid. So it looks like there's some weird stuff going on here that might not be exactly what we're expecting. It turns out that as long as you're staying in the same row of the periodic table, electronegativity is the bigger factor. So moving horizontally, in other words, more electronegative does make you more acidic. So that just comes down to if we end up with a CH3 with a negative charge, that's going to be way less happy about it than F with a negative charge because F is more electronegative. But moving vertically, what actually, weirdly enough, ends up being the more important factor is atom size. So if you imagine the conjugate base of these four halogens, like I minus versus Br minus versus Cl minus versus F minus, it turns out I minus is actually better at carrying that negative charge because it turns out being a bigger atom actually helps more than being more electronegative. Okay, and that actually comes down to partly negative charge stabilization, and also it turns out just the bond between the H and the halogen is so weak for these larger atoms because the atom's so large that the bond length is quite a bit longer than it would otherwise be. That the H just like drops right off, is barely on there to begin with. Okay. So HI is actually going to be the strongest acid that we'll see in the pKa tables. Okay, so questions about that one? Okay, cool. So I guess like you'll notice the same trend between oxygen and sulfur. Sulfur, even though it's less electronegative, is still more acidic than water is, or than oxygen is. Okay, so in the notes I have sort of a hypothetical like kind of gen chem bond dissociation energy kind of step. I don't think I'll go into that level of detail in this lecture. It's pretty much, if you remember these trends, it just explains the whole pattern. Okay. So next up is the resonance effect. Okay, so it turns out that for reasons that have to do with pChem, the more area a charge can spread out over, the more stable it's going to be. And this is what's called the particle in a box model. The bigger the box gets, the more stable the charge is. Okay, so we already know that we can use resonance to move a charge around. And this is actually the two examples that I put up here without explaining why one of them was more stable. So if we have some carboxylic acid here, and we take away a proton, not only can we show it just as the deprotonated negative charge on the oxygen there, but we can actually kick that up here get the negative charge up on that oxygen instead. So pretty much we don't really have a negative charge that's locked down onto this one oxygen atom. We have half a negative charge here and half a negative charge here. So it's sort of smeared out over this entire carboxylic acid part. Just as a heads up, we didn't show this when we were looking at just resonance by itself before, but a lot of the time if you're using resonance forms on something that happens as part of a bigger reaction, a lot of the time you'll just draw square brackets around the whole thing and say something happens, and then you get to this molecule that's really like an averaged together version of these forms. Okay, so we can draw it as these two resonance forms, or, and it looks like this printed kind of confusingly in the notes because the dotted lines are not that clearly visible, but you can do that sort of partial bond way of drawing it that we've seen a couple times before. Okay, so for carboxylic acids in general, depending on what R is, and we'll see a few examples of that in just a second here, pKa here could be anywhere from 0 to 5. But if we take away that resonance option, and just have a CH2 there instead, now when we deprotonate, negative charge is kind of locked down onto that one atom, and there's nowhere for it to go. So this one, the pKa is going to be 16 to 18 usually, and again varying depending on what exactly R is. Okay, so questions about that sort of factor? Okay, cool. So number 4 here is dipole induction. which Loudon calls the polar inductive effect. But both of these are kind of hinting at the same thing. It's caused by polar bonds. Nearby the acidic site, the atom that loses a proton. And this one is usually going to be the most subtle out of the 5 factors, but if you've got a lot of this effect going on, it can still outweigh the others. Okay. So we know that this molecule, which is acetic acid, by the way, the same thing that makes vinegar smell like vinegar, is 4.76 for pKa. But if we put in, instead of a CH3 out at the end, we have a CH2 with a single fluorine atom on it, we know that fluorine, being the most electronegative atom, is going to sort of pull electron density out towards itself out of that CF bond. So carbon ends up a little bit short on electron density, fluorine ends up kind of rich on electron density. The interesting thing is that this carbon is not entirely happy about that, so it's going to sort of kick the effect down the chain a little bit, just it'll get weaker with each step. So the next carbon-carbon bond we have is also kind of a little bit polarized out in that direction. So it's not as strongly polarized as the CF bond here, but it does still pass down some of the delta positive charge that it's getting. Okay, so on this carboxylic acid, and it may help to also show like what happens when it gets deprotonated. So once we go to having a negative charge here, we're pulling just a little bit of charge density away from this end of the molecule, which means that the negative charge is getting distributed just a little bit out through the bonds of the molecule to the far end of the chain. So you got just slightly less than a full negative charge because of what's going on further down the line. Okay, so the pK of this thing, acetic acid with 1 fluorine on it, just having that 1 fluorine on there drops this by 2.6, or drops this by about 2 pKa units. Okay, so you might be wondering, well, we've got 3 different H's on there originally. Why don't we just swap them all out for fluorine one at a time? Or you might not be wondering that, but too bad, because we're going to do that anyway. Okay, so this one, acetic acid with 2 fluorines on it, or difluoroacetic acid. This has even more of the same thing going on. Now the carbon's getting tugged, or its electron density is getting tugged out towards both of the fluorines, which means it's left even shorter on electron density, which means it's kicking that sort of scarcity down the chain a bit, which is good for stability if you have an oxygen with a negative charge that you want to stabilize later on once this thing loses a proton. So here the pKa is going to be 1.24. Or we could go to 3 fluorines on here, which ends up being a surprisingly low 0.23. So this thing has 3 different directions the carbon's electron density is being pulled, which adds up to a pretty big dipole pointing out towards the left end of the molecule. Okay, so this one is actually acidic enough that it frequently gets used in reactions where you want some acid catalyst added, but like HI or HBr might do some weird side reactions that you don't want to deal with. So this one is commonly used. It's called trifluoroacetic acid, or TFA. Okay. So questions about this series? Okay, cool. So one other thing we can look at. So in this case, we're just swapping out H's for F's that are all like only one atom away from the acidic end of the molecule. What if we look at doing stuff that's further and further out from the acidic site? All right, so here's sort of a longer carboxylic acid. It's pretty close to acetic acid. It's about 4.82. And I'm just going to draw 4 copies of this to use as like a starting model to add stuff to. Okay, cool. So 4 copies of the same thing right now. What I'm going to do is start throwing a chlorine atom on. First out at the far end, then 1 atom closer in, then 1 atom closer in from there. So 3 different places it could go. It turns out this is not a huge effect, but it does change the pKa measurably. So 4.82 to about 4.5 to about 4 to about 2.84, which is pretty close to what happens when we have a single fluorine on that atom next to the carboxylic acid group instead of a chlorine. Okay, so just by having like 3 different structural isomers with the same parts, but just scooting the chlorine closer and closer in, I can change the pKa a couple units that way. Okay, so questions about that? Okay, so one thing that is a little bit sort of vague is a lot of the time with the resonance effect up here, you could also argue that part of the reason the negative charge is stabilized is also because you have induction from this other oxygen up here. So most of the stabilization is due to resonance and being able to push the charge around entirely, but it's a little hard to separate out. Maybe like a little bit of the extra stabilization is also coming because you have some dipole induction from the other O. But you can also just get dipole induction going on by itself with no resonance either. Okay. So the 5th and final factor that we're going to look at is called the orbital effect. So this depends on the hybridization of the acidic atom. Okay, so we already know that when we make hybrid orbitals, we're averaging together whatever those hybrid orbitals are made of. So for instance, an sp3 atom, its bonding orbitals are going to be 25% s and 75% p, which we know because we're blending together 1s and 3 p's, so s makes up a quarter of the total, or 25%. Okay, so it turns out that the more s character an orbital has, the more stable a lone pair is going to be. Because on average, for a given energy level, the s orbitals are held in just slightly closer to the nucleus. Okay, so the way that we can sort of look at this trend is just by going through some carbons in different levels of hybridization where they're each losing a proton. So for example, if we try to pull a proton off of, what hybridization is this carbon here? sp, right? Yeah. So if we pull a proton off of there, we're holding a lone pair in what also turns out to be an sp orbital. So that's 50% s, which is more stable than if this thing tries to lose a proton. Here, the lone pair is in sp2, which is 33% s. And that's going to be even less stable than this thing, a carbon that's sp3 hybridized. Because there, the lone pair is going to be only 25% s. Okay, so this actually alters the pKa unit dramatically. Here, pKa is about 60, which again, you might see a few slightly different numbers cited because this is so not acidic that it's also hard to measure. This one's usually going to be about 45. And I guess for all of these, it depends on what R is. And this one's usually going to be about 25. So just by changing the hybridization on the carbon atom, you're going up by about 35 pKa units, which is a huge difference in acidity. So sp3 hybridized carbon is going to be generally the least acidic thing that we'll ever deal with. Turns out you can still make this happen. You just need special chemistry to get around how unlikely it is. And we'll cover how to do that later on. Okay, so questions about this factor? Whoa. Okay, cool. So in general, if I ask you to rank things by acidity, I'll try to keep the variations all within one category. So it might be like mostly the same structure, but then you have like sp versus sp2 versus sp3 carbons. Or you might have like varying dipole effects only, or varying atom effects only. Okay. So that pretty much actually wraps it up for acid-base stuff in this chapter. So yeah. So I think during the last 15 minutes, I'm going to get started a little bit on chapter 4, which the chapter notes are posted on the website as of a couple days ago. Okay, so I'm going to shuffle around the order of coverage a little bit for this chapter because I think it makes more sense to cover sort of structural naming first and then get into the geometry around the carbon-carbon bond. Okay, so chapter 4, we are getting into alkenes. So we spent chapter 2 looking at alkanes. And it turns out that alkanes, there's not a whole lot you can do with reactions with them. We'll only ever see like one reaction pretty much that we ever do with alkanes. Alkenes, you can do a ton of stuff with them. So we're not just looking at alkenes for structure like we did for alkanes. We are also, in this chapter, getting into full-on reactions for the first time. So we've seen a little bit of acid-base stuff, like one-step reactions, but we're going to see full-on multi-step reactions for the first time in this chapter. Okay, so as a reminder, alkenes are things with carbon-carbon double bonds. So naming is first up. Okay, so all the rules from alkane naming still apply, but they're sort of overridden. We're going to slap a few extra rules in there that take higher priority. Okay. So we're still going to go through the process of determining the longest or the principal or the parent chain. But calling it longest chain might not be the most accurate thing anymore. So parent chain might be the better phrase to use moving forward. Because we no longer care about having the longest chain, the one with the most carbons in it. We care first about having the one with the most double bonds in it. So we want the one with the most double bonds, even if that means this is going to be shorter than we would normally pick. Okay. So if there are multiple chains that are tied for having the most double bonds, though, then you pick the longest out of those. Okay, and then if that still doesn't settle it, then you default to the rules for alkane naming, where you look for the ones with like the most branch points coming off of it. Okay, so an example of how that might look. Okay, so in this case, if we were going for just longest chain, we'd choose 1, 2, 3, 4, 5, 6, 7 carbons. But that doesn't include any actual double bonds along the backbone. So they have to be like in the actual chain, not just hanging off of it. So in this case, we got to pick starting up here. So you end up with a parent chain that's 1, 2, 3, 4, 5, 6 carbons, not 7. Okay, so questions about that part? Yeah?
By double bonds, you just mean carbon-carbon double bonds?
Yeah, so double bonds to other stuff are different functional groups, which we'll cover when we do the chapters on those functional groups. Okay, so once we've got our parent chain nailed down, then we want to name each group coming off the parent chain. This is pretty much the same as before, but we will see a couple new groups. So let me draw a parent chain that has 2 double bonds of its own, so we're not conflicted about what to name as the parent. Okay, so one possibility is this substituent here that's just 2 carbons that are double bonded to each other. This one is called vinyl, and that's actually where the name of vinyl records comes from. It turns out, I draw it over here, this thing is vinyl chloride, and you can do a reaction that links a whole lot of copies of this molecule together into a long chain called polyvinyl chloride, or PVC, which is what, or one component of what albums or records are made out of. We'll talk more about how to do that later on. So that's a vinyl group. And this thing, which is the same but with an extra carbon, so 3 carbons total, is the allyl group. I guess when I was learning this, I remembered that it looked sort of like a capital A a little bit if you drew it hanging off at that angle. But whatever works for helping you remember it. Okay. Everything else in this is same as before, so like methyl, ethyl, butyl, whatever. Questions about this? Yeah?
When you number the parent chain,
Mm-hmm.
you're in the first molecule,
Mm-hmm.
you start closest to the nearest double bond.
Good question. So that's actually step 3, which I'm going to get into, which is numbering the parent. Okay. So, yep, you're exactly right. We do want to start at the end closest to the first double bond. Or, if both ends are equally close, we want to start at the end closest to the first point of difference. Okay, so you might have an alkene, multiple alkenes along the molecule, and you just want to have like as many of them as close to the starting end as you can. Just as a heads up here, when you number an alkene, you're going to count it as the first carbon of that double bond you encounter as you go along. Okay. So, and then I guess just to finish it up here, if this still doesn't resolve it, if both ends have exactly the same alkene placement as you go along, then you just fall back on the old alkane names, alkane priority rules. So minimize substituent locations, like we've done before. Okay. So again, for this one, which has an allyl and a vinyl. So the parent chain, I have a bunch of different potential options, but every choice I pick is just going to have 2 different carbon-carbon double bonds in it. So I'm going to choose this as my parent chain. If I start numbering from this end, I got double bonds at carbon 1. So here, let me write the numbers up. 3, 4, 5, 6, 7, 8, 9, 10. This is 1, 2, 3, 4, 6, 7, 8, 9, 10. So if I'm using the top set of numbers, I have alkenes starting at carbons 1 and 9. here I have alkenes starting at carbons 1 and 9 again, because it's always the first carbon of the alkene that I encounter as I go along the chain that I'm counting. So that doesn't resolve it. So then it's just down to, do I want groups at 4 and 6 if I'm using the bottom numbers? Or do I want them at 5 and 7? So obviously 4 and 6 is going to be the better choice. So I'm going to use these numbers down the bottom here. Okay, so give me just 1 minute here to finish this up. Actually, you know what? That's a pretty good stopping point. Okay, so on Monday we'll pick up from here. Garrett will cover the last bit of how to put the naming together.
Hi. I just have a quick question. So I know in your APPM for math or whatever,